Let's continue our discussion of enantiomers by looking at chirality. And this really fits because if we have enantiomers, or if a molecule has an enantiomer or multiple of them, then we call that molecule chiral. If it does not have an enantiomer, we call that molecule achiral. One of the ways that you can identify an achiral molecule is if it has an internal mirror plane. And if it does, the molecule will not be chiral. Let's go back to the chiral side. Over here, you'll see that I've drawn up two versions of 2-bromobutane. One where the bromine is coming towards us and one where the bromine is going away from us. These molecules are enantiomers of each other. Or another way to say that is they are chiral. Each of them has what is called a chiral center. A chiral center is a carbon or some other molecule or atom that has 4 objects around it that are different from each other. And we can look at the 4 objects that are different here. Behind here, something that I did not draw in, is the hydrogen. So that's one object that's on this particular carbon. There's a bromine, there's a methyl group here, and there's an ethyl group. All of those are different from each other. And therefore, since there are 4 different objects around that particular carbon, that is a chiral center. Sometimes those are also called stereocenters. A stereocenter is an atom where switching 2 groups that are attached to it into a different position will create the other stereoisomer. So and each of these has one stereocenter. The chiral centers could be carbon. It's very commonly a carbon. But again, we could have a nitrogen if it has 4 groups around it, which would necessitate it having a positive charge. Silicon could also be another example. Now, just because a molecule has a chiral center does not mean it's chiral. So an achiral molecule can have chiral centers, but I think I'm getting a little ahead of myself on that. So let's look at the model kit here, just so that we can see a little bit better what this looks like. So here's the one where the bromine is coming towards us. And I also have the mirror image of that where the bromine is going away from us. And the hydrogen in this case is coming towards us. They are mirror images of each other. If I put this in the correct, if I align that, right? So now they're mirror images of each other. And they are not superimposable. So there's no way for me to make these both match up with each other. There's a jumbled mess here, but you can see here when I try to line them up, the bromines are on opposite sides of the molecule. So that is an example of a chiral molecule. And this is the chiral center or the stereocenter, whichever you would prefer to call it. You can call it either in this case, because it has a different group around on each side, right? On all four positions. Now, I mentioned that an achiral molecule can have a chiral center or multiple chiral centers. It can't have just one. If it has just one, it will be chiral. So I should write that down over here. If it has just one chiral center, it will be chiral. It can have multiple chiral centers and be chiral, but it can have multiple chiral centers and be achiral. So let's make an example of that. So in order for me to do that, I'm going to rotate this around so that I get the right position here. Like so. So this carbon still has 4 different groups around it. It has a hydrogen, it has this ethyl group with the additional bromine on there, but it doesn't change the fact that it's different from the methyl group over here. At the same time, this carbon has 4 different groups around it. It has a methyl group there, it has the same similar ethyl group here with the bromine there and the hydrogen. So there are 2 chiral centers on this molecule. However, if we rotate this around, which is allowed because this is a single bond, and if I align this nicely so that we can see, there is a mirror plane here. And if we have an internal mirror plane, the entire molecule will be chiral, even though there are chiral centers contained within it. These kinds of molecules have a special designation called meso. A compound is meso if there are 2 or more chiral centers but there is a mirror plane of symmetry. Because it has a mirror plane of symmetry, overall, this molecule is achiral, even though there are 2 chiral centers in it. Now, if I were to switch, so instead of the bromine being here, it's down here, right? It's opposite. this no longer has an internal mirror plane of symmetry. I can try to look at it a few different ways, but this just doesn't match up, right, anymore. And if I try to align it so that I could get a mirror plane here, then this is not in the same position. That's a hydrogen, that's a methyl group. If I were to reflect this would not be the same on this side. This is an example of a molecule that has two chiral centers and is chiral. Hopefully this isn't too confusing. It's one of those things where having a model kit is very useful. Now, you may think, well, if I have a chiral molecule, I have to have a chiral center. Well, as you've seen over here, we can have molecules that do have chiral centers, but are achiral overall. So you may guess that it's possible to have a chiral molecule that does not have a chiral center. That's true. Now, this is a little bit less likely to happen than the meso compounds. There's a lot of those. And there's a few that do not have a chiral center, but are chiral. And one such example is an allene molecule. So allene has a carbon that is double bonded to an additional other carbon. Right? So it has this double bond carbon structure. Now, if all of these were hydrogens on there, like in the case of allene, this would be achiral. But we're going to put some substitution on there. Let's say that we have a hydrogen there and we have a fluorine here. And then on the other side, we have a fluorine there and a hydrogen here. Now, I'll go ahead and draw the mirror image of this. There we go. At first glance, this may look like we can superimpose these or there's a mirror plane in here somehow. But remember that when we're bonding with double bonds, we have to use a p orbital to do between these two carbons, and then we have to use a different p orbital for the bonds between these two carbons. And p orbitals are perpendicular to each other. And the model kit does a reasonable job of showing that. So I have made a model of both of these. I just had to figure out which one is which so that I could get that right. So here's the one on the left. And you can see here, the fluorine is going down. It's in the paper. The hydrogen is going up in the plane of the paper. And then we have a fluorine coming out and a hydrogen going in. And I have constructed the mirror image of this. And you can see how all of these atoms are not contained within the same plane. There's this plane that's kind of like the plane of the paper, and then there's the one that's perpendicular. And that's a result of these p orbitals. It has to use a different p orbital to do the second bonding because this carbon's already used one of them to bond here, and then this second one has to be perpendicular for the other carbon. So that's one of the features of these allene molecules. So you can see here that these are mirror images of each other. Now let's try to superimpose them. So when we do, I've lined up the hydrogens and the fluorines on this end of the molecule, but when we look at the other end, they're on the opposite side. And so these are an example of a chiral molecule, but there is no chiral center on here because there's no carbon that has 4 different objects on it. Yet it is still chiral. I would say that that is one of the interesting examples of this process or this phenomenon, but it's less common than having just, say, a chiral center or maybe multiple chiral centers, and then it's just not meso, and then it is a chiral molecule. That's more common than not having a chiral center, although chemists find those examples interesting because it kind of breaks a typical rule. And so we find that intriguing. So this is a little bit about chirality and the differences between chiral molecules and some molecules that are chiral. Keep in mind that having chiral centers does not guarantee that the molecule will be chiral. However, having only one chiral center will guarantee that the molecule will be chiral because it cannot have an internal mirror plane if there's only one. You have to have at least 2 in order for us to have a meso compound. Tetrahedral stereocenters are called chiral centers. That is where we have 4 different objects around a central carbon or other atom in the middle, in the case of this nitrogen. And we can switch the 2 compounds to the other enantiomer by merely moving 2 groups. In this case, for example, I've moved the position of the bromine and the hydrogen. And I can do that on a model kit by simply pulling the bromine and the hydrogen out and exchanging their positions. And that will generate the other enantiomer. So, thank you for joining me for the video on chirality, and we'll see you in the next one.